Let me go figure out what we're talking about. So we're going to go back and do some quantum mechanics. So talk about the swap circuits. Yeah, so the first example I want to do is what's called dense coding. So the history of this field is, so there's a bunch of optics experiments in the 80s looking at kind of trying to probe the foundations of quantum mechanics, and this is part of where Bell's inequalities come from. But in those days, they thought that the biggest application was going to be communication protocols. So the idea was you make entangled states, and then nobody would be able to interfere, because if an eavesdropper kind of tried to interfere in the communication, you would lose the entanglement, and the communication system would break. So this is kind of in that setting. So the idea is you set up a Bell pair state of photons, and then you figure out some communication system where you're sharing. It depends on sharing the Bell state, the entangled state. So so this is an example of, people call it dense coding. It's a little bit confusing because you're really sending one qubit. So one qubit, and you're actually communicating two classical bits. But before you send the single qubit, you share an entangled state. So beforehand, you share an entangled Bell pair. So there's actually a little bit more information than just sending a qubit. It sounds like too good to be true, right? You send one qubit and you communicate two classical bits. But really, you're also beforehand sending this classical thing, this entangled state. So we're going to try and communicate two classical bits. So we have 0, 0, 0, 1, 1, 0, 1, 1. So those are the possible things. And beforehand, you start with this, which is the usual thing. You start with this. We have two people, and because this is a communication thing, so we have Al and Bob. This is usually Alice and Bob, or Alan and Bob, or Alan and Bobby. I mean, kind of replace, it's A and B. Are the two people. So Alice wants to communicate one of these to Bob, and they start off with one of these. So one of them has the first bit, and the other guy has the second bit, but it's an entangled state. So right. So right. So let me start with what happens. So yeah. So since I'm using this blackboard as an eraser, and I'm not going to go to the other blackboard. Actually, I need to be able to have room right here. So let's make it tails. So Alice is going to do some operations on her half of the Bell state. So Alice's data operations. So the Photon table, and the value that she wants to send are going to be 0, 0, 0, 0, 1. And so she only has the first bit. So if she wants to send, so here's the send to 0, 0. He doesn't do anything, so that's two identities. And if she wants to send this, then she does a spin, does a flip of her bit. And if she wants to do that, then she changes the sign of the first bit. And if she wants to do this, she uses the Cowley Y. And so let's figure out what happens to the Gall pair state. So the resulting state. So it's not changed. So we can just write down what happens here. Nothing happens. Now we flip the first bit. If we want to send 0, 1, 0, 1. And this one, it changes the sign. The second one. This is the P operation, does that. And this one multiplies by I and changes the sign of the first one. So it's 0, 0. Oh, it also flips it. And this one. So that's what you get. So notice that Alice is only operating on her half of the Bell state, right? So they've already shared the Bell state. Okay, so now then now she's going to send her qubit. So remember, this is she gets to send a qubit. So she's sending her qubit, and so now Bob has both qubits. Okay, so right. Okay, so we need, that's the resulting state, and now Bob receives the first qubit. He's already got the second one because they shared that in advance. And what he does is he applies C naught with the control bit. Is the 0 and the target. So let's do that on these. So I need to make another list here. So I guess we can rewrite those. So this is what Bob receives. And he's got 1 over the square root of 2 0 plus 1. And now he does a C naught 1 on it. It's a standard C naught. So what happens when you do a C naught? You flip the second bit if the first bit is 1, right? And so what he gets is plus 1 0. That's correct. Yes. And then right, he also then applies the Hadamard, and then he measures both bits. So first he does this, then he applies the Hadamard, first bit, and then so let me write down what Bob is actually doing. And so what Bob does, once he receives the qubit, he does this. Hadamard, and then he measures. These are Bob's operations. let's finish filling the table here for all the cases. So the second case we've got 1, 0, plus 0, 1. We need to apply the Hadamard on the C0 on it. So you flip the second bit if the first bit is 1. 1. And now the third one is this, which is 0, 0, minus 1, 1. Minus 1, 1. Flip the second bit. The first bit is 1, which is this. And the last one is I, 2, or 1, 0, minus, well, it's actually minus 1, plus 0, 1, right there. And flip the second bit, right here, and it's a minus 1, plus 0, 1. Okay, now we have to Hadamard the first bit. So that is going to, there's going to be a list of things here, but it helps if you rewrite the state. If we simplify, so you notice that this is 0 and this is 0, and so I can rewrite this as 0 plus 1, 1, 0. And this is 1 plus 0 with a 1. And this is 0 minus 1. With a 0. 0. And this is minus 1, 0, O times 1. That. So it's a lot easier to think of what happens to a Hadamard if you apply the Hadamard. So Hadamard on 0 gives you 0 plus 1. And then if you square the Hadamard, you get back what you started with. So this is 0 times 0. And the same thing is true here, because this is 0 plus 1. And this one, it's a 0 minus 1. So that's the, when you Hadamard 1, you get that. And then if you Hadamard it again, you get the 1 state back. And then this one is minus, that's the same as this, but with this I in front of it. So we can put an I here. 1 plus 1. And now when we measure both bits, you get 0, 0, 0, 1, 1, 0, 1, 1. Which is what Alice said. So let's review what happens. So we started with, you make a bell state, and then you send one piece of it to Bob, and Alice keeps the other piece. Then Alice does these transformations depending upon what she wants to send. Then she sends her half of the entangled, her qubit from the entangled thing to Bob. And then Bob does these transformations and then measures both bits. So if somebody had interfered in the middle, it would have lost the entanglement. And so there's no way for anybody to interfere with it. And it's considered somewhat efficient because only one qubit was shared in order to transfer 2 classical bits of information. So that's the idea. So that's why it's known as dense coding. So kind of weird. It's like, you know, so and then this example, there's more communication protocols that are based on it. So the idea being making it efficient to transfer information, but very hard to interfere with. So, so this is one of the first examples for communication protocols based on entangled states. Okay, so let's move on to talk about Bell states. So, yes. So let's talk a little bit more about the EPR paradox. So, so we've been using these Bell pair of states, sometimes called the EPR state. So, so I remember we mentioned this before with this is the idea of the EPR paradox, where you make a state, make this entangled state, and then you send half of it, the first qubit to one person, and then you send the other qubit to the other person. And it looks like a paradox because measurement on one half of it determines the measurement on the other one. So this bothers people because it feels spooky. It feels like it's, you know, it feels like it's determining. It feels like it's teleporting information faster than the speed of light. So when we get around this by saying it's not causal, in the sense that the wave function, it's there's no actual information transferred faster than the speed of light. What's happening is you're giving something that has correlated probabilities, but that one person measurements, they're not actually giving any information to the other person. Only afterwards could they determine that they measured similar things. So that's one way around it. So another way around that might be more palatable is to say, what if there's a hidden variable? So this is hidden variables. So what if at the same time as you compute this, or you make the state, there's something else being set up that's determined, and it's going to determine the outcomes of the measurements. And so these are known as hidden variable interpretations of quantum mechanics. So the idea is that there's no randomness involved, there's no probabilities. Really what's happening is being generated something else that's simultaneously being generated that you're not measuring, but that other variable is going to determine the results. And so it's another interpretation of how would you explain that in quantum mechanics we describe the physics in terms of a wave function where the coefficients are determining the probabilities of different measurements. So the thing with the hidden variable theory is that it's ruled out. By violations, what's known as violations of Bell's inequalities. And so so that's another set of examples to look at, is what are Bell's inequalities for particular situations. So that's something that I'll show you with two photons, and then instead of measuring the state, you're measuring polarizations, and so the spin up state turns out to be a vertical polarization, and the spin down turns out to be a perpendicular polarization. So it behaves similar to our two-state atom, but the interpretation is polarization angle. So so that's so that the experiment, and that the experiment gives you a particular ratio. So what that particular experiment is, you generate the Bell pair state with photons, and then you have two observers. Again, it's Alice and Bob, or Alan, Bobby, whatever, and they choose choose angles to set their polarization measurements, and so the classical example is you have three possible polarizations to set your polarization, and they're randomly choosing whether so it's this way or 60 degrees or 60 degrees in the other direction. And Alice choosing randomly some orientation for her polarization measurements, and Bob is too. And then later on, they get together and they look at see how many times did they agree with their measurements and how many times did they disagree with their measurements. And you take the probabilities of those, what's the probability of them agreeing, and you compute it using a quantum mechanical model, and you get a particular number. And then you try and redo the prediction with the idea that there's a hidden variable setting the chance that they'll get the same measurement, and you're going to get a different number. And the quantum mechanical one would be lower than the hidden variable one. And so if you rewrite it in terms of an inequality, saying that there's a probabilities for pairs of measurements, and they all should be greater than something if there's a hidden variable theory, and you measure below that, you violated the hidden variable theory and shown that it's incorrect. That's the idea. Yeah, so hidden variables theory is one class of interpretations for quantum mechanics, and what we'll show is that Bell's inequalities and experiments based on them rule it out, essentially. So what other interpretations are there for quantum mechanics? And so the one that most people follow is the Copenhagen theory. So Copenhagen. Or it's not, I don't know, maybe it's not a theory, it's an interpretation. So what are the ingredients? So let's just kind of summarize. So here's the story. We have the EPR paradox. And this raises the question of how do we interpret quantum mechanics? A in there, quantum mechanics. So one of them is hidden variables. This is rule. Actually by violations. Okay, so then let's move on to the Copenhagen interpretation. Okay, so what's the Copenhagen interpretation is maybe kind of a set of guiding principles. And so we have the Bohr rule. And the idea is that the wave function is probabilities for measurements. So these are for outcomes of measurements. Then we have the correspondence principle. What's the correspondence principle? H bar goes to 0. We recover classical mechanics. I think it's H bar goes to 0. Yeah, that makes sense. So, or H, this Planck's constant. So really what's the correspondence principle is that you recover classical mechanics in some limit. So we could be a little bit more careful. I mean, so this is there's some history of this, right? So I mean the idea is like we start with, if you look at the history of different physics theories, Newtonian mechanics should reduce to physical laws that make sense to us. So when you look at Newton's laws, where you assume that the natural state of something is to move without stopping, to stay at a constant velocity. But on Earth, we have a reference frame where things tend to slow down and stop to be with us while we move on the Earth. And that's because there's lots of friction and there's drag. But Newtonian mechanics, when you add in like the forces and understand them, the theory is consistent with that. And then things like to track the orbits of planets, they're consistent with this nice theory of you have a universe square law for gravitational forces and the trajectories are all consistent with it. So the idea is you have this more beautiful general theory that when it's given the additional physics or the right limits, it reduces to the experimental results that you measure accurately in the lab. So if you think of general relativity in the limit, that reduces to Newtonian gravity. And if you look at special relativity in the appropriate limit, it reduces to Newtonian physics. So the idea is quantum mechanics should do the same thing. In some limit, it should be consistent with classical physics. And what does that limit mean? So one of the limits is that number of energy states, instead of being quantized, things are continuous. Things stop interfering with each other and they decohere, so things stop being phase dependent in some limit. And then this idea of wave function collapse, like instead of acting like probabilities, we have a high probability for it to act like a classical particle in a particular location. So correspondence principle, we expect that to happen. And then other things that are part of the Copenhagen interpretation are called, what sometimes people call complementarity. And this is the idea of this is that you have things that you can't simultaneously measure. So you think of the Heisenberg uncertainty principle. So it's not necessarily possible to simultaneously know everything about a particular physical system. know all quantities describing the system. So the Heisenberg uncertainty principle, where you have delta x, delta p is something at each part. I mean, there are classical analogs like the uncertainty in your ability to measure a period and a frequency. You can think of that as an uncertainty relation, and that's a classical thing. If you have a sound file and in it is some frequency, your ability to measure that frequency depends on the length of time you have of the signal. So if the signal is really long, you can measure the frequency really, really accurately. And if the signal is really short, you only get a piece of the wavelength, and so you don't really know what the wavelength or the frequency of the signal is. So, so there are classical analogies to the Heisenberg uncertainty. Okay, so that's like the basic framework of the Copenhagen interpretation. But these are basically the postulates that we work with quantum mechanics. And so this is not really under a real philosophy or anything, or it's not really fundamental principles, and so that sometimes bothers people. And then if you look at all the different branches of physics, this correspondence principle causes problems because we have, in general relativity, we have a limit of it giving us the equation of gravity, which those theories are both very accurate. And we have relativistic limits. But GR is not consistent with quantum mechanics in those incarnations. So there's some details like correspondence principles, yeah, but the overlying theories, the more general theories, don't all agree with each other, even though they do reduce to non-relativistic and classical limits. So it could be that our just following the Copenhagen interpretation is limiting us in the sense that we're not going to find the true theory that explains the world. So now there's a lot of different possibilities. And one of them is like the many worlds interpretation. So let's mention that. So get rid of the Copenhagen interpretation. There's the many world interpretation. So the many world interpretation is the idea is that you've got you may have a wave function that's described as probabilities, and then supposing you measure something, and then the wave function collapses based on the probability of for you to measure a particular thing. At that moment, it's like the universe splits, and one universe measures one thing, and the other universe measures another thing. So it's like you've got two universes. So you're starting off with the same universe, and the measurement happens. So now there are two universes going with both possibilities. So, I mean, I guess that's okay. It's not very predictive because once you're in one universe, you don't get to communicate with the other one. So, thinking about, and this is maybe more of a problem when we talk about cosmology. You can think, well, let's describe the wave function of the universe. If I have 100 wave functions, then I'll have these possible outcomes. Each one will have, we'll get various probabilities of things happening. But then you can say, well, that doesn't make any sense because we're only in one universe. It's like I can't go measure something in another universe because I'm not in that universe. So it's not very predictive. So if you're diehard like me, you would say, I don't really care because there's no experimental ways to tell. So what do we do about the cat? Yeah, so the cat, so we can think about these different interpretations with the thought experiment. So this is cat, and he's either dead or he's alive. Right? He's alive. So, and you've probably seen before this stuff. So the thought experiment comes from Einstein, I think, and Bohr, and they were concerned about the process of measurement. And so the thought experiment is you have a box and you can't see it, and you can't hear it, and you can't do an X-ray of it or anything. You're not allowed to get any information about what's in the box. Well, so what's in the box is this cat. So put the cat here. Let me see if I can draw a cat. Here's the tail. Here's the cat. And he's sitting in the box with some kind of radioactive source, and the source has some probability. So you can get a radioactive thing that has some half-life that it will decay or not. And so you set up the experiment to run a particular length of time. The probability is a half that there will be a radioactive decay, and half that there won't. And if there's a radioactive decay, there's some mechanism inside the box that will kill the cat. And or I think like some kind of acid or something, and Einstein like gunpowder, whatever. In any case, there's some device that kills the cat. And then the observer, so the cat is either dead or alive, and you don't know. And so that's why you described it as a superposition state. Well, what does it mean for a cat to be both alive and dead at the same time? So that bothers people. And then once you open the box, then you're the observer, and so then you can tell. You observe the cat, and the cat is either dead or alive. So, yeah, so so in quantum mechanics, we usually divide processes into two pieces. So you have unitary evolution, and then you have measurement. And so while things are evolving by unitary evolution, there's no uncertainty in the problem, it's deterministic. But your evolving probabilities, not amplitudes, that when you square them, give you probabilities. And then when you do a measurement, you collapse the wave functions. So so in the Copenhagen interpretation, as long as you're not observing the cat, the superposition state is fine. But I mean, maybe you can get around this by saying, well, the cat's actually interacting with a lot of things, and you could actually get information about. There's no way to really make a box absolutely isolated. So you can't get any information. Shake it, X-ray it, listen. Particularly with Einstein's view of the gunpowder, you hear a click or something. Like, and so one way out of this is actually what happens is that there's a lot of interactions and the wave function decoheres. So decoheres means it stops being in the superposition state because there's a lot of degrees of freedom. So within the Copenhagen approximation, you have this process of decoherence that collapses the wave function. And so we don't necessarily need to have a superposition state of half dead and half alive cats. In many world interpretation, you just have two universes. If it's a dead cat and a live cat, you're in one or the other. So, but you can't communicate from one universe to the other. So yeah, so it used to be that these were the only types of quantum mechanical interpretations, the Copenhagen, the hidden variables, and the many worlds. And now there's dozens. So if you are interested in, and it's actually kind of very mixed in philosophy now. So if like philosophy, goes on and on. Even the wiki goes on for pages past what most physicists pay attention to. Or not all. Some physicists really get into it, actually. So the philosophy is attractive to things. Okay, so let's look at the Bell inequality now. Give you guys a feeling. So I'm going to talk about EPR. Polarization measurements. And so the whole point of this is to show Bell's inequality. So we have a polarizer. So instead of using 0, 0, and 1, 1 for quantum states, we're going to use the Bell's error state or the EPR state like this. So we call it the EPR state, or the Bell pair state, or the cat state. And this is just equivalent to this. But the up arrow is meant to be vertical polarization, and the horizontal arrow is meant to be horizontal polarization. And if you put a polarizer, then the idea is that polarizing either passive or absorbed. And so if I put the polarizer vertically, so if I have a polarizer in the vertical direction, then it's a projection measurement. And if this is in the vertical direction, yes, if I do this, I get 0. So this, it's like a projection measurement. And if I have the polarization in the horizontal direction, then I have the opposite. So this is 0, and this is my state. But I can rotate the polarizer by various angles, and then it will be just as if we use the Pauli X type of thing. So for example, so with the Bell pair state, we can say we give one photon to Alice and the other photon to Bob. And so one photon goes to Alice. Other one, Bobby. And then, but now Alice can choose what angle to measure the polarizer with. So suppose she measures in this case, but Bobby decides to measure in some other, he rotates his polarizer. So, what would happen if we did that? So one way to decide what happens if he rotates his polarizer is to transfer into a rotated frame. And so we can take the wave vector and transform it by some rotation, which is equivalent to saying rotating his polarizer of the wave vector. what's this rotation vector going to look like? It's just actually a rotation. So cosine theta, we get the sign that I have in my notes. So this is only operating on the second qubit, or it's not a qubit, second photon. So let's move it here. And I'm just going to multiply this matrix on the second part of it. Cosine theta, up, that, cosine theta, up, around this way. Yeah, that's right. This way. So I put a matrix here. So I have to tell you how I'm defining the basis. So this is equal to 0, and this is equal to 0, 1. So when I multiply cosine theta times this, it's like it's a vector, and just like we did with the qubits. And then we have a minus sine theta. This and cosine theta. So let's measure the first qubit. And Alice is measuring the up down. And measures theta, perpendicular to theta, which is theta equals 2. So we're measuring the first one, it's cosine squared for this state, plus sine squared for that state. So cosine squared plus sine squared is 1. And then there's square root of 2. I have to square that, so it's a half. And so Alice has a half probability of measuring it in the up state, and that's a pass. And the half of measuring it horizontal, which is even good. But Bob, we rotated the coordinate system, which is equivalent to kind of rotating. We rotated the state, so that's kind of equivalent to rotating Bob's polarizer. But Bob has cosine. Let's see. So up. Yeah. Let me make sure I got this right. Yeah. So now we're measuring the second one. It looks like it's cosine squared and sine, unless I have them flipped. Should be, looks like I'm getting cosine squared, cosines, I'm getting cosine squared plus sine squared. Maybe I have it backwards. Let's see, so this one is up and up, cosine squared, sine squared. But if Bob measurement measures, then we have this one plus this one, right? For up, which is cosine squared plus sine squared. And now I'm confused. Well, something to fix in my lecture notes, because what I'm supposed to get, even though it's not consistent with that, is that Bob is supposed to get a cosine squared measurement if he measures them up, which is rotating by 65 by the angle theta, and sine squared is the probability that he has it the other direction. So that's what you're supposed to get, even though I don't think that's consistent with what I've written there. I'm not sure what the error is. So if theta is 60 degrees, then cosine of theta is a half, and he should have a probability of 1/4 to measure in his 60-degree state, and he should have 3/4 the probability of that. So this would be a pass, and a 3/4 probability of absorb. So I'll try and fix that. Figure out what I went wrong. So the setup is you make a whole bunch of photons that are entangled like this in the EPR state, and they're entangled, and you just send lots of them to Alice and Bob, and they're making lots of measurements, and so you're getting a probability, and for each measurement, they're allowed to choose the angle of their polarizers. And so there's bunches of ways you can set up the problem. The simplest one is that you allow 3 possible types of polarization. You allow your polarizer to be vertical, or you allow it to be at plus 60 degrees or minus 60 degrees. And then the probability should be 1/4 if Bob picks his 60 degrees away from Alice's. They should have a probability of 1/4 to get the same measurement. So right. So let's put all the possibilities of what the different measurements can be. So this setting is the quantum EPR measurement. In this particular setting. So Al can choose her polarizer in 3 different ways. And then 3, yeah, and then I have this one, which is the plus 60, and then I have the minus 60 degree measurement. And then Bob also has 3 different possibilities. So I put 3 here and 3 here and 3 here so that I can give all possible combinations. And then this and this, so that's all 3 combinations. And this, and this, and then this, and this, that. Now here they're the same, and so we write down what the probability that the measurements agree. So since those 2 are exactly the same and it's a Bell state, the measurements have to agree. So we put a 1 there, and here they're both aligned in the same direction, so that's equivalent to rotating both. I can rotate the states simultaneously, and they should wind up looking exactly the same. So the probability should be the same, that they measure the same thing. And similarly down here, it's 1. And so now if you go through that, the probability is 1/4 that they're going to measure the same thing. And so you can put 1/4 for all the rest of the possibilities. So it's 1/4, and then 1/4, 1/4, 1/2, and then there's another 1/4. So the table of all the possible things that can happen. And you don't really know how they're choosing their polarizers. They're supposed to be randomly picking angles to put their polarizers in. So we have to take into account all of these possibilities they're equally probable. So the probability that they agree here is, so there's 9 possibilities. So there's 1, 2, 3, 1/3 of them have a probability of 1 agreeing. And 2/3 of them have a probability of 1/4. That's all there is. And so if you add this together, the probability, taking into account all of these cases, is a half. So, so that's the main result. Like working through the polarizers with all these possible choices, you get a prediction for what Alice and Bob are going to measure. You can go into the lab and check the prediction and find out that it agrees with this number. So the quantum prediction is correct. So the next part of this argument is you say, what if we had a hidden variable theory? And then what happens is you get a different prediction for the probabilities. And you'll get a different number. And so the hidden variable theory, which is the next piece of this argument, will, it doesn't work. And so for the simplest hidden variable theory, you just say, well, I'm going to choose 3 hidden variables. And then that will give me, you go through all the possibilities. You just get different numbers in these columns. What happens is you get a larger number. And so that's one hidden variable theory. But once you have one hidden variable theory, you can show that you can change the probabilities for each of the variables in the hidden variable theory. And no matter whenever you change the probability distribution, it's just as if you're weighting the different cases differently. But you have the sum of things that are positive that give you some number. And there's a minimum that sum can be. And so, so that's how Bell derived this thing called the inequality law, where he showed that for any hidden variable theory, there was a number where if you added up 3 different cases, you had to measure something larger than that. So that's what's called Bell's inequalities. And there's various, and this is in the case of polarizations where we're restricting the polarization choices for 3 different settings. Bell's original derivation, you're allowed to choose any angle for your polarization settings, but you can also come up with similar ones where you're measuring spins up and spins down, and then write things in terms of pairs of agreements. And then the main result is the quantum mechanical number is under the limit. And so you rule out any possible hidden variable theory, which is the point, right? It's not a hidden variable theory. All of them get ruled out in particular experiments. So let's go through the hidden variable example. And it's basically the same argument, except without a mistake in the wave function. And place this hidden variable. So we can't just have two variables because there's 2 photons. So we're assuming there's maybe a 3rd piece of information. And so we have so what possible things could you have for so we're going to assume you've got 3. And we could, for any choice of these hidden variables, then you have to decide whether whether you're likely to have agreement or not. So supposing your hidden variables give you pass means it passes through the polarizer for all of these three choices. So this is like you've chosen all three variables, so they're going to allow pass. Then what's the probability that they're going to agree? And that's 1, because they're all allowing all three variables. So we're going to give you both photons passing. So now we just have to go through. So what if your choice of hidden variables for those three orientation angles are all going to give you absorbing photons? Then the probability that you are agreeing should be 1. If it's not 1, it's not really going to agree with the expected experiment. But now we have all these different possibilities. So what if the hidden variables do this or do this? So how many ways are there to choose whether the variables allow you to pass or get absorbed? Well, there's 8 ways to do this, right? So this is 1, 2, 3, I have one more AA. And then I had 3 more different A values, P, PA, and A. Okay. Yes. So we just have to figure out what's going on with these 6 possibilities. So yeah, okay. So let's look at this one. And then this one has 2 P's and an A. And all of these cases have 2 of one thing and 1 of one that doesn't agree. And so once we figure out this case, we'll be able to, by symmetry, just say all the rest have to be similar. So, so I'm just going to take the PPA possibility. So the hidden variables pass, and absorb for those 3 polarizers. So if Al, so we have Al can choose polarizers in 3 different directions, and Bob can choose polarizers in 3 different directions. So we have 9 possibilities again. And then we have this, and this again. So it's the 9 possibilities we worked through before. And so now I just need to go through this table. And so it's PPA, so this is going to be PP, right? And then this one is so PPA. We pick this one. So I just need to keep looking at this table. So PPA is this way and that way. So I'm going to get PP. This one is this one and that one. So it's PA with that. And then this one is this one and this one. So it's AP. And this is this way. So it's AP. So these are the measurements. And then these are whether they agree or not. And so this is yes, yes, no, no, yes. Well, we can keep doing this. So I did 5. Let's see, this one, this one. So this one is 1 this way, which is an A. And then so this is an A, B. And this one is 1 this way. Wait, it's not an A, this one is PA, or it's P. Let's do this right. So these 3 are P's. This one is PPA. This one is P, PA, and now we have that right? Sorry. Yes, yes. No. PPA, PPA. You're right. This one is, oh wait, these are wrong. Yeah, okay, so that's why I didn't agree. So it's yes, yes, no, then yes, no, yes, they agree, they don't agree, they agree, they don't agree, they don't agree, they don't agree, they agree. Okay, good. So 1, 2, 3, 4, 5. 5 lines. Okay. So now we can go fill in this table. 5 minutes. We got what I wanted. Yay. 5 minutes. So there's 2, this is a table of 8, and there's 6 5 nights. So now we can compute the probability that they agree. Use 1 8, so it's 2 8 times 1 plus 6 8 times 5 nights, because there's 6 possibilities for the probability of 5 nights. And if you work through that, you get 2 2s. So, right. So, putting all this together, this particular hidden variable theory, where we just said our theory should be equivalent to having 3 things that are chosen by what they do with polarizers, gave us a probability that 2 measurements should agree should be 2 pairs. So this was the hidden variable theory. And what we had for the quantum mechanical setting, we had 1 half. So you can see that the hidden variable theory, if you can do something bigger than the quantum mechanical setting. So, so you can write this out as the probability for 2 things. So these are the two polarizers plus 2 different choices of polarizers plus 2 different sets of polarizers is greater than 1. And so this is the normal form for Bell's inequality, although usually this is written out like this. So you have to take, how do you get it to work? Right, so for our setting, for 2 polarizers to agree, we had this probability of 1/4. And so for the quantum mechanical setting, we had 1/4 plus 1/4 is greater, well, should be greater than equal to 1. But when you add the 3 up, you get 3/4 that's less than 1. So this was the probability for each one to agree. So the quantum mechanical setting violates Bell's inequality, and you have to turn this into probabilities of 2 particular measurements agreeing to. So that looks like it's less than 1, but it's not. If you multiply by 3, and use the single pair thing in order to get it to be consistent with this particular form. So when you look at what people call Bell's inequalities, it winds up having this particular form. Okay, I could make this clear, so I'll work on it. But anyways, we're out of time. So that is the, oh right, I guess there's one more thing to mention. And that's, right, so the one more thing to mention is we chose a particular choice for how our hidden variables would work. But you can weight the probabilities for the hidden variables any way you want, and it will not change the limit of the inequality. And so the final result is actually stronger than just saying, here's a, so when I was working through this, you know, when you go through all the different choices for a particular type of hidden variable, you feel like, well, this can't be a really solid result because I'm having to make all these decisions on how I choose the hidden variables. But once you've set it up, you can show that you could change the probabilities of how you chose them, and you still get the same minimal inequality. And so the result is actually quite general. But the last step has to do with changing the weights for all of the decisions that you made in going through the variable table. So the fact that the inequality is in reality violated is a very strong result when you think about it that way. So it really eliminates the hidden variable interpretations. Okay, so that's it. We're out of time. And next time we'll talk about teleportation and more black box problems. And meanwhile, you have a problem set using Q-tip to work on next week. Hey, so we had a question, but I never heard you guys. Somehow the speaker didn't give me a, can you do more than Q2 bits? I'm not sure where that question came, but it was right a while ago. But I think everybody's gone now.